Okay, it should start recording now. And I will start with just writing scribbles. So what do we want to look at? Today we will look at entanglement. And entanglement is a special type of correlations where there's a system which we refer to A and B. And they are far away. So the distance is non-zero. So they cannot directly influence each other. And if B, so let's say Bob, if Bob wants to influence system A, so Alice, then the time for that it has to be non-zero in the sense of speed of light. So D will be the distance. And then T has to be such that speed of sound or speed of light is so this time needs to be longer than D. Okay. And there is something weird in nature that there's this notion of non-locality. So if if Alice has a quantum system modeled by HA and Bob has a quantum system modeled by HB, then if we want to make a quantum model for the whole thing, we would say that they will have a state in the Hilbert space, which is a tensor product of H and HB, okay? And that's a very basic tutorial, so I will actually explain what this is. So HA will be span of a certain set of states, at least two. One, and it might end here, or it might go longer. And for Bob, we will do the same, okay? So we would say that the dimension of HA is dA, and correspondingly for Bob. This is actually important, and we will say that this is finite dimensional local Hilbert spaces. And finite dimensional quantum systems is in some way a certain restriction. People also work on infinite dimensions. And here I will just give you a couple of keywords about also research areas. So if it's not finite, then what? And for example, it could be harmonic oscillators. Where the Hilbert space is just the different states in the harmonic oscillator. And in principle, it goes all the way until infinity, okay? And this we will, this is actually called then continuous variable systems. Okay, systems. And this is more or less equivalent to quantum optics. So quantum optics, or for example, something called GKP codes, which is very nice if you want to match quantum optics with quantum info. That's a very nice subject. I will not say more what this is. And for example, if you have defects in crystals. We were talking in the quantum engineer's guide to superconducting qubits that you can have a quantum LC circuit, and that would be a harmonic oscillator here. And if you put a Josephson junction, you here a capacitor actually. Then you bend up this kind of harmonic oscillator modes, and we have this detuning and harmonicity and so on. Okay, Defects in crystals, they don't have this. So there's another X. You don't have a Josephson junction for that stuff. But you can, for example, think of some cat state encodings or GKP codes in general and work with them as qubits. So can be more difficult, but we are getting better in physics, and you can also work with that, okay? So harmonic oscillators, continuous variable systems. But today we will be only doing this, yeah? So we will be happy. Another keyword that is important is C-star algebras. And maybe I won't say more about this. Watch out for this subject because it's elegant, but it's very difficult to do something new in C-star algebras, but can teach you a lot about linear algebra, matrix analysis, and so on. Okay, so let's say the go-to book would be Bradley Robinson. But as I said, watch out, because reading this might be just equivalent to a master thesis. What did I else want to say? Quantum field theory. And quantum field theory is a different problem because I could take a harmonic oscillator and it can be a representation of modes inside of a box. Okay, so if you have a particle moving here with coordinates x and p, and it's somehow moving in the box, if you quantize this, you will do the quantization in terms of some eigenmodes. Okay, and basically the 0, 1 levels would be which kind of oscillation is going on in the state. So I could have here cosine pi k z. This coordinate is z. And here I could have some principal eigenmode, eigenvalues, or base states. Yeah. And this kind of base state would be the principal mode, and here I have to have k. Okay, so that's how a harmonic oscillator can be changed into real space. It's not exactly why we call them continuous variable systems, but you see that that's when you have infinitely many modes, you can parameterize a discrete function space. So always think of the Fourier transform as, for example, e to I k z, and then some numbers ak here. And then if we quantize, we would more or less use the similar formalism, only use operators in terms of it, instead of ak here, for example. So you see how a discrete sum can parameterize a continuous function. And that's more or less the weird stuff that starts happening if you have infinite dimensions, because maybe some of you worked with convergence of this stuff. Is you have absolute convergence, and absolute convergence goes wrong for quantum fields. Okay, and for all those setup be, there's actually no difference, but I will just say it's C2, so it's 2 qubits entangled with each other. And I will give you the best example for an entangled state. It is 0, tensor 0, plus 1, tensor 1. Okay. So what's going on here? When we are writing HA tensor HB, it doesn't mean that this is the set of states of the form A tensor B. And those we would call product states. You can also have superposition states. And today we will prove a theorem. No, today we won't manage to do it, but we will prove a theorem saying that phi cannot be written as phi would be equal or is not equal to phi A tensor phi B. So there's no way to choose where phi A would be in the A Hilbert space and then phi B would be in B Hilbert space. And let me give you one example. Let's consider the state psi, which would be 0 tensor 0 plus 1 tensor 0 plus 0 tensor 1. And your task is to find phi what find A0 plus B1 such that our state here psi is equal to phi tensor phi. So what I'm doing here is I'm giving you a hint how to find that this state. So what it will say is that this state, despite of having superpositions here, it involves a certain number of superpositions. Its superpositions in the state are not equivalent to entanglement. Entanglement is a much more difficult property. So even though you might at first think, okay, this might be entangled because it has some superpositions, still it's a product state. Okay, and I'm giving you a hint that on the Alice Hilbert space and B Hilbert space, the state is the same. In general, they could be different. Okay. So I'm checking the chat. Okay, nothing in the chat. So I will pause maybe the recording. Can I? Okay. So very good. The solution is hopefully not too hard to see, but if you consider this state, plus 1, and then divide by square root 2. I should probably put the normalization somewhere. So here by square root 2. Okay, I will be forgetting normalization sometimes. So if you consider this, then if this wasn't clear for you that that this doesn't hold true, then it's useful to do the exercise to see that basically the tensor product is associative. So if I forget about this square root 2 here, I can write 0 tensor plus 1 tensor plus, and then you get the idea that this will be exactly psi. Okay, so we have a tensor product of two plus vectors. Okay, and just to be clear, I mean, this plus state is, this would be 0, this would be 1, then the plus state is here. That's the meaning on the blocks here. Okay, and now we have two of them, and we are explaining now that tensor products are kind of weird. And basically you should go to Wikipedia and study the definitions of operations for the tensor product. What we used here is in some way linearity or associativity and so on. Yeah. So some definitions like this to justify those calculations so that you get this. So this shows that even if in the state you have superpositions, those are superpositions, a plus state has superpositions, so the state inherited the superpositions, then still it doesn't mean that you will have entanglement, okay? So you can see it nicely also for this state. And this I won't be calculating anymore. It will look like it has superposition because plus state has a superposition. But an important thing is that a single qubit state will never be entangled. Why? Because entangled with what? Yeah. And my entry to this discussion was this A and B. So entanglement is always between two systems. You need to select two systems that ideally are also separated. Okay, but you have a notion of two separate systems. A single qubit could be at most entangled with itself, but that's not very meaningful. Okay, so the plus state has or is okay. I will write it properly. Involves quantum effect superposition. Entanglement is more than superposition. That's what we learned here. It's more than superposition. Okay, but you need to have superpositions for entanglement. Okay, good. Maybe there will be something more to say, but I'll open a new page. Okay, no questions. Good. So now we will talk a little bit about local operations, and you will learn a little bit more about the tensor product. And at some point we will learn what's going on with the CNOT or Bell states and so on. Okay, so now one question. So we saw a tensor HB is not the set of product states. There can be also those superpositions. Okay, so if I do HB, then is it E to A tensor E to B? Okay, a minute of thought for you. You can place your bets, yes or no, in the privacy of your mind, because whatever your answer is, I mean, it will change how you view the discussion here. Yeah. Another problem that I want to show is, so I will still put a question. Okay, I won't be putting a question mark here because this is true. And the difference is that tensor products behave a little bit as products, and then basically a tensor product of linear vector spaces is a new linear vector space. So this is an element of this, and it's even in some way a basis element. And now because the tensor product, so the full linear vector space that arises from the tensor product, is a vector space, so I can be adding things that are explicitly coming from those individual tensor products. Okay, and if I have something like this, then it turns out that in general, this is not, I don't know, EA plus E prime tensor something. Okay, So you don't only have a notion of tensor products of states. You have also a notion of tensor products of operators on the states. And let me explain a little bit why this is. We denote linear operators on a Hilbert space like this. So this is linear operators. So for example, linear operator on HA, which means it's mappings of phi into some phi bar. Okay, it's changing the states. So this would be matrices A, which are 2 by 2 in our explicit case, 2 by 2 matrices, linear operators. Okay. And then we can exponentiate them and so on. So what we can consider is the space of operators like this, but this is also a linear vector space. So what I wrote here is that basically you take the tensor product of those two linear spaces of operators, and you will have here A tensor B, something like this. But you will also have here a tensor B plus A prime tensor B prime. Okay. And that makes it non-trivial. And that's why we don't have an equality here, but we will have an equality here. And now I want to prove that. So that's the calculation for today. You can think for a second how you would go about proving this. And I will start typing. Okay, so n from 0 until infinity, 1 over n factorial. Let me get there's something in the chat still. Okay, good. There was a good answer for one of the questions in between. That's our definition. And now, one of the most important properties of the tensor product is that we have this property. Okay, so 1 second to think about this. What does it mean? That's what you would find on Wikipedia. So now you can check yourself whether you would be able to learn this if you would be on your own. Okay, so what does it mean is that if I have two operators which are coming, so A tensor B is a linear operator on the AB product space here, on the tensor product of those base spaces. Okay, so I take two such operators and I multiply them, because I could also call it a C operator and I might forget that this is an AB operator. Okay, and that's why so basically this is some C operator, and you see that this is isomorphic to L to C to power 4. Okay, so we took 2 by 2 matrices on 2-dimensional spaces locally, 2-dimensional, 2-dimensional, and the operators that act on Alice and Bob's system together, they are 4-dimensional. So I could forget that there was Alice and Bob and just call them a system of Charlie. So Charlie is somehow like, you know, encompassing those two, and Charlie would have a 4-dimensional system. So you would have 4 by 4 matrices. 4 by 4. Okay, 4 by 4 matrices. So you have the C, and then you take C and multiply it with C prime, but you see that C and C prime were tensor products of operators. They were product operators, and they remain a product operator because it's of the form A prime prime tensor B prime prime, which means I can find an operator on A and an operator on B such that if I take their tensor product, I will get C times C prime. Okay, This is just, this here is definition. But we need to be able to use the definition well, okay? So what's going on here? Here we are in, this is looking like C prime multiplied together, but we want to write it as kind of this A prime. So we want to go here, okay? So in between you would use induction, you can use on your own induction to do this, but you should see that this will be A to power N and B to power N. Does this make sense? I think it does. Did I mess something up? No. Okay, wait, I messed it up. Did I mess it up? Yeah, I messed it up. So I didn't want this one. Now I wanted to show you for B equals identity. This will be true, okay? So now we see, okay, this doesn't simplify further, so it's a good exercise. Further. And and in general, such an operation would be actually entangling. Okay, I messed up the order of what I want to show you, but okay, I'm prepared enough to tell you more. So now let's take the example. Let's take the example, special case. B equals identity. So E a tensor identity. So what does it mean? You could think of a Hamiltonian acting trivially on Bob's part and doing something for Alice, okay? And we want to ask whether there will be something happening for Bob, and what we want to find is that this will be E to power identity, E to a tensor identity. So let's say some evolution where the Hamiltonian is acting trivially on Bob's part would be an evolution of Alice and doing nothing on Bob's part. Okay, so that's the preparatory calculation that we want to do. And we will see that this simplifies in this case. Okay, so let's see how to prove this. So we have n from 0 until this is n, 1 over n factorial, a to power n, tensor identity to power n. So I keep writing because this is just rewriting stuff mostly. Identity to power n we know, there will be a to power n. And then we can use some sort of induction argument to say that there's associativity of the tensor product. And this identity to power n equals identity, we can pull out from here. And we get our result e to a. This is this. Tensor this identity. So pulling out the identity still needs some kind of associativity. Yeah. And let's see how it plays out, because this is actually important. This is, let's say we have some state psi, and we apply this a tensor identity here. Then we can do a basis decomposition. So I will have e to tensor identity 0. So some a00 tensor 0 plus ea tensor ea0 1 0 tensor 1. A lot of writing here. A1 0 1 tensor 0, and as I'm typing here, scribbling, you can think about how to simplify this stuff. How do you simplify this? Okay, so hopefully you found out that you can use this formula that we just derived, that used the derivation. And then if I have here a tensor B where A and B is 0 or 1. Yeah. Then I can use the definition of the tensor product of operators. So applying a product of operators. So here I'm applying a tensor product of two operators to a tensor product of two vectors. And it's defined, this is actually a definition of the tensor product of operators. It's defined as identity on B. Here note tensor product, yeah. Which means that I get some new state A prime, tensor B, okay? Which we see that nothing happened in B, because that's the definition of the identity, okay? So we saw that A tensor B doesn't simplify further. We landed the hard way. I tricked you, saying that it will be equal, okay? But we saw that A tensor identity is splitting in this very nice way into identity. In general, unless, no, even if I commute, it doesn't make sense. Eh? But now the question is, what happens if I have something like this? Okay. That should hopefully work. Yeah, I know how to prove this. And we're fine. I will wait maybe in the chat, maybe you can think about. I said I don't know how to prove it. So unless you don't trust me, you will say that this is not equal. Okay, well, I will just continue. First of all, we will show something about the commutator. So today I'm quite patient. But unless you know all those operations where they are coming from mathematically, you cannot work on entanglement because tensor products are important in entanglement. Because entanglement is weird, and if tensor products are weird for you, then tensor products are weird for you, then you cannot distinguish the weirdness of, working with those operations from the weirdness of entanglement. Yeah, so you need to have this craft of working with that small field of mathematics. Okay, so we are commuting. So what do? A tensor identity plus identity tensor B is equal to EA tensor identity times E identity tensor B. Okay, this times is multiplication in linear operators on, for example, this C4 space. Yeah, so those are those larger matrices. So you could view this as, again, E to C times E to C prime. You don't need to know anything about the tensor product there. Sometimes it's good to forget it. Yeah. So a matrix product is not a tensor product. Yeah. Okay. I hope I didn't add to confusion. Anyway, this we know that it's E to A tensor identity. And then identity tensor B E to power B. Okay. And then again, we just put this together. Okay, I will do this E to power B. And this is just local matrix multiplication with an identity, so nothing changes. Okay, voila. Those smileys don't work in this with this pen. Okay, voila, we finished, yeah? Which means that, how do we interpret this? If these are Hamiltonians, so what happens if these are Hamiltonians? HA is equals to a tensor identity. It means some energy cost for Alice, but nothing for Bob. Okay, so in that sense, we would say that this is a tensor identity is local to Alice. Okay, that's when locality comes in for the first time. And we get this notion of locality, and you see that even though you take here an exponential of 2 of those operators, the way it plays out, thanks to all this commutation stuff, the way it plays out is that you do it locally using A and locally using B in this case. Okay? I hope you're very, very happy with it. I don't need to say more because this is just interpreting the equations, right? So you're doing your own physics in your mind, so you can try to, find the best way for you to see. But what I'm saying here is that this is this idea of locality. One last question to you as you're studying this and deepening your understanding here. What happens here? And in general, no simplification. In the interpret in Alice and Bob systems, but there would be also an interactions happen only if those agents, Alice and Bob, if they are close by. So, okay, the way we go about it is you have a nonlinear crystal. Linear crystal, I think that's how it's pronounced. You pump it with some energy. And then here locally, 2 photons emerge into directions, and then they propagate. So the interaction here was local, and then the free space propagated it until Alice and Bob are space-like separated. Okay, but they can share but the state for this joint system, this is a joint system here. The state here would be psi. Let's put the square root 2 because there was the Nobel Prize for showing experimentally that you can realize such states in nature. And suddenly they share some non-local feature because you can have effects such as teleportation. Unfortunately, it's not static teleportation, so it's a different kind of teleportation, and they share entanglement, which is a new kind of correlations in nature. Okay. So just as an outlook, today we prepared your mathematically to show that there exists no A and B such that AA tensor AB on psi is equal to phi tensor phi prime molar. Okay. And basically what this means is we cannot disentangle with local operations. What we can see today is we can disentangle with e to a tensor b, which is not equal e to a tensor e to b in general. Okay. And this would be equal to EA tensor identity plus identity tensor B. So those are two different things. Okay. That's what we saw today. So we can do this disentangling because you can consider here a Hadamard transformation. And here, where are we flipping? We are flipping on this one. And this would be a C naught. So you start with 0, you start with 0, and you get your entangled state psi out. I will link the Kibo notebook for this. You can try in your browser with Kibo to do those transformations. Kibo, just to write what I said now, this is a package for trying out different circuits. If we write this together, this will be some unitary operation U, and basically this operation U will be of some form e to I a tensor B plus a tensor identity plus B tensor identity, stuff like this. Yeah. Here I'm putting an I because here I'm choosing a already Hermitian so that they look like Hamiltonians. Here we were just working with exponentials. I mean, in the end, you should think of them as anti-Hermitian so that those are unitary. And why anti-Hermitian is because if you take a Hamiltonian with an I, that I makes the whole thing anti-Hermitian. Yeah? So we didn't restrict any generalization. I was just teaching you about how tensor products encode locality, yeah. And for this we don't need unitary operations. In the end, whenever you apply an operation to Alice and Bob, it would be unitary, yeah. But so that's why this appears here, because I started drawing circuits, and that's a constructive example how to disentangle the Bob Alice and Bob state. So the bell pair, we disentangle it because if I would apply the inverse of this circuit to psi, I would get a 0-0 state. Yeah. So there would exist an operation that disentangles those two. Okay. And what we get is basically something about operations. So there are classes of operations, local operations. And those local operations don't change entanglement. Today we showed the converse, that a non-local operation, so local operation is a tensor A, non-local would be a tensor B. Why is it non-local? Because it acts directly on A and B, which to implement physically would need to be they would need to be close by. Okay. I mean, you can use entanglement to teleport some interactions, but that's a different story. Okay. Checking no questions. Okay, good. So, okay, so we gave an example of a non-local operation that disentangles. Then it's kind of good also to build entanglement. So we have this CNOT circuit. And next week we will use something called something that I will tell you next week. But there's a nice mathematical theory that then builds up to really see that you cannot write this, yeah, because we also started with the example that I wrote down a state, and you have to think a little bit to see that this state is not entangled, and the plus tensor plus state is a product of two plus states, yeah. So there's a way of checking it numerically without checking all possible combinations. You can do linear algebra in a very nice way. So this is what we will do still for one more session, and then we will have this fundamental proof that you cannot disentangle with local operations. You cannot destroy entanglement here like this. Okay.